What if I told you something invisible is dragging our entire galaxy through space at an unimaginable speed? Not just us, but hundreds of thousands of other galaxies, all racing toward a single point in the darkness like moths to a flame. For decades, astronomers have been baffled by this cosmic anomaly, a gravitational force so powerful it defies explanation. They call it the Great Attractor, a mysterious region of space with the mass of tens of thousands of Milky Ways, lurking behind the dense stars of our own galaxy's center, hidden from view. And what it's doing challenges everything we thought we knew about the universe's structure. This isn't just some distant curiosity. Right now, you, me, and everything we've ever known are hurtling toward it at 14 million miles per hour. Yet despite decades of research, we've barely scratched the surface of what's truly out there. The Great Attractor is just one piece of a far grander puzzle, a web of colossal superclusters, vast voids, and invisible threads of dark matter that weave the universe into an architecture so immense it makes our galaxy seem like a speck of dust. These are the large-scale structures of the cosmos, the hidden scaffolding of reality itself, and they hold secrets that could rewrite the story of existence. So today, we're embarking on a journey to the edge of understanding, where the laws of physics twist into the unknown. We'll unravel 30 mind-bending truths about the Great Attractor and the cosmic web, from the shocking forces bending galaxies into rivers of stars to the eerie, dark flow that hints at something even more enormous lurking beyond the horizon of our observable universe. This isn't just about distant space, it's about our place in a mystery so vast it redefines what's possible. Buckle up, because by the end, you'll never look at the night sky the same way again. The discovery of the Great Attractor reads like a cosmic detective story, one where the clues weren't something we could see, but something we could feel. In the 1970s, astronomers noticed something bizarre. Galaxies in our local universe weren't just drifting apart as the expanding universe should dictate. Instead, hundreds of thousands of them were all moving in the same direction, as if pulled by some unseen hand. It was like watching leaves swept up by a hidden river current, only this current was flowing across hundreds of millions of light years. The culprit, an enormous concentration of mass lurking about 250 million light years away, in the direction of the constellations Centaurus and Hydra. But here's the twist: we couldn't see it. Our own Milky Way's dense disk of stars, gas, and dust, a region astronomers call the zone of avoidance, blocks our view like a cosmic blindfold. Imagine trying to study a mountain range through thick fog, knowing something massive must be there because of the way everything around it bends and swirls. That's the challenge scientists faced. Early observations relied not on light, but on motion, tracking the strange velocities of galaxies with radio telescopes, peeling back the layers of the cosmic onion to infer the presence of something colossal. The numbers were staggering. This invisible behemoth had the gravitational pull of tens of thousands of Milky Ways combined. Yet for decades, it remained a shadow, a titanic mystery hiding in plain sight. And the deeper astronomers looked, the stranger the story became. The Great Attractor wasn't just pulling us, it was part of something even larger, a knot in the vast cosmic web where galaxies gather like cities along an invisible highway. But why does this matter? Because finding it forced us to rethink how mass is distributed in the universe. We used to picture galaxies scattered randomly like stars in the night sky. Now we know they're threaded along filaments of dark matter, drawn together by gravity's invisible hand. The Great Attractor was our first glimpse into this hidden architecture, proof that the universe isn't just expanding, it's flowing, shaped by forces we're only beginning to understand. And somewhere beyond it, the cosmos has even more secrets waiting to be uncovered. Picture the universe as a vast, invisible battlefield, one where gravity is the ultimate weapon, and entire galaxies are caught in a struggle too colossal to comprehend. At the center of this cosmic tug-of-war sits the Great Attractor, a gravitational monster so powerful it's bending the fate of our entire local universe. The Milky Way, Andromeda, and more than 100,000 other galaxies are all being dragged toward it at speeds that defy reason. 14 million miles per hour, fast enough to cross the Atlantic Ocean in less than a second. But here's what makes this even wilder. We're not just falling toward the Great Attractor, we're part of an even larger movement, the entire local supercluster, a sprawling family of galaxies stretching over 110 million light-years, is caught in this flow like leaves caught in a hurricane. Astronomers call it the dark flow, this eerie, synchronized motion of galaxies all streaming toward the same unseen destination. It's as if space itself is a conveyor belt and we're just along for the ride. What's truly humbling is realizing how small our place in this struggle really is. The Milky Way weighs in at an impressive 1.5 trillion times the mass of our Sun, but compared to the Great Attractor, we're practically insignificant. This hidden leviathan commands a gravitational pull equivalent to tens of thousands of Milky Ways combined. To put that into perspective, if you imagine the Great Attractor as a black hole, which it isn't, but just for scale, its event horizon would swallow our entire solar system without even noticing. And yet, even the Great Attractor isn't the end game. Recent observations suggest it's just a waypoint in an even grander journey. Beyond it lies the Shapley Supercluster, a staggering collection of galaxies so massive it might be the real heavyweight champion pulling everything toward it. This means our cosmic fate isn't dictated by one force, but by layers upon layers of gravitational influence, like nested Russian dolls of dark matter and destiny. So what happens when we finally reach this invisible maelstrom? Nothing dramatic, at least not for billions of years. Galaxies don't collide like bumper cars. They merge, dance, and swirl in slow motion over cosmic time. But the fact remains, right now, every star, planet, and speck of dust in our galaxy is part of a migration older than life itself, swept along in a current we're only beginning to map. And somewhere out there, beyond the edges of our vision, the universe's largest structures are still shaping the story of everything we know. Just when we thought the Great Attractor held the title for most powerful cosmic force in our neighborhood, astronomers uncovered something even more extraordinary, a gravitational giant so massive it makes the Great Attractor seem like a mere stepping stone. Meet the Shapley Supercluster, a sprawling metropolis of galaxies 650 million light-years away, containing roughly 10,000 times the mass of our Milky Way. This isn't just another cluster, it's the largest known concentration of matter in our observable universe, and it's locked in an invisible tug-of-war with the Great Attractor for control over the fate of our entire galactic neighborhood. For years, scientists assumed the Great Attractor was the primary force dragging our local supercluster through space. But when they mapped the motion of galaxies with unprecedented precision, they found something startling. The pull from Shapley was even stronger. Think of it like two black holes orbiting each other, except instead of black holes, it's two titanic collections of galaxies and dark matter, each bending the fabric of space-time to their will. The Great Attractor may have been the first mystery we uncovered, but Shapley is the hidden puppeteer behind the curtain, pulling strings we didn't even know existed. What makes this rivalry so fascinating isn't just the scale, it's what it reveals about the universe's structure. Dark energy, the mysterious force accelerating the expansion of space, should be pushing galaxies apart. Yet here we are, caught between two gravitational behemoths fighting against that expansion, proving that on cosmic scales, gravity can still dominate. It's like trying to swim against a river's current while two whirlpools fight over which way you'll go. Here's where it gets even stranger. The Shapley Supercluster isn't just pulling us, it's pulling the Great Attractor too. That means what we once thought was a single point of attraction is actually part of a far grander flow, a river of galaxies streaming toward an even deeper gravitational well. Some scientists speculate this could mean there are structures beyond Shapley, even larger and more distant, warping the cosmos in ways we can't yet detect. This cosmic duel forces us to confront a humbling truth. We've only mapped a fraction of the universe's true mass. Every time we think we've found the edge of the puzzle, another piece emerges, rewriting the rules. And somewhere in the interplay between these titans, between the push of dark energy and the pull of dark matter, lies the answer to why our corner of existence moves the way it does. The universe isn't just expanding or contracting, it's dancing, and we're only just beginning to hear the music. The most unsettling truth about the Great Attractor isn't just its immense power, it's that we're essentially staring at a ghost. 80% of the matter creating its gravitational pull doesn't emit light, reflect it, or interact with ordinary atoms in any way we can directly observe. This is dark matter, the universe's most elusive architect, weaving an invisible scaffold that holds galaxies together while remaining utterly transparent to our telescopes. Without it, the Great Attractor's gravitational grip would make no sense, like watching a marionette dance without seeing the strings. So how do we know this shadowy substance exists at all? The answer lies in cosmic sleight of hand. When light from distant galaxies passes near massive objects like the Great Attractor, it doesn't travel in a straight line. It bends, warped by gravity, like a straw appearing crooked in a glass of water. Astronomers call this gravitational lensing, and by mapping how background galaxies appear subtly distorted, they can trace the outline of invisible mass like detectives dusting for fingerprints. The results are staggering. For every ounce of visible matter, stars, gas, planets, there's 4 times as much dark matter sculpting the cosmos behind the scenes. Supercomputer simulations reveal just how bizarre this hidden structure might be. Imagine a vast, tangled web where dark matter clumps into halo-like clouds around galaxies, with tendrils stretching millions of light years between them. The Great Attractor sits at a knot in this web, a place where filaments intersect and gravity pools like water in a valley. These models show ordinary matter as mere decoration on an unseen framework, like Christmas lights strung along a tree's invisible branches. Yet dark matter's dominance raises an eerie question. If we're hurtling towards something mostly made of material we can't see or touch, what does that mean for the future? Unlike black holes or stars, dark matter doesn't collide or emit radiation. It passes through itself and ordinary matter like a phantom. As our galaxy plunges deeper into the Attractor's grasp, we'll glide through these shadows undisturbed, even as their gravity reshapes our cosmic neighborhood over billions of years. This paradox, being pulled by what we cannot perceive, is what makes dark matter both frustrating and fascinating. It's the universe's ultimate tease, proof that most of reality isn't just unknown but unknowable by conventional means. And as simulations grow more sophisticated, they hint at something even stranger. That dark matter might not be one single substance, but a family of particles with behaviors we've yet to imagine. Every clue we gather about the Great Attractor isn't just mapping a destination. It's revealing the hidden rules of a game we've only just begun to play. Trying to study the Great Attractor is like attempting to read a book through a fogged-up window, only in this case, the fog is our own galaxy. A thick band of dust, gas, and countless stars sprawls across the Milky Way's center, creating a blind spot astronomers call the zone of avoidance. This cosmic curtain obscures nearly 20% of the sky, and for decades it hid the Great Attractor from view like a stage hidden behind velvet drapes. Stare toward the constellations Centaurus and Hydra with an optical telescope, and all you'll see is a murky haze, our galaxy's crowded core standing guard, refusing to reveal what lies beyond. But here's the twist: scientists are nothing if not resourceful. When visible light fails, they turn to other wavelengths. In the 1990s, a breakthrough came from an unlikely hero infrared light. The 2-micron all-sky survey, or 2-mass, scanned the heavens in infrared, a wavelength range that slips through dust like sunlight through smoke. Suddenly, galaxies lurking behind the zone of avoidance flickered into view, their heat signatures untangling the mess of foreground stars. It was like switching from a flashlight to night vision goggles, revealing shapes in the dark we never knew were there. Then came X-rays piercing even deeper. The Rosat satellite, designed to detect high-energy radiation, spotted colossal galaxy clusters in the Great Attractor's grasp regions so hot they glow in X-rays like celestial spotlights. These weren't just ordinary galaxies, they were giants bound together by gravity in numbers that explain the attractor's pull. Step by step, astronomers peeled back the Milky Way's veil, exposing a hidden metropolis of matter. What's astonishing isn't just that we overcame the obstruction, it's what the zone of avoidance taught us about our place in the universe. We're not passive observers floating in clear space. We're embedded in the very obstacle that once kept us ignorant. Every discovery behind that curtain reminds us how much lies beyond our immediate sight, waiting for the right tools to reveal it. And as technology advances, who knows what other cosmic secrets still hide in plain view, masked by the glittering sprawl of our own galactic backyard. We used to think our Milky Way sat at the center of a modest galactic neighborhood until 2014, when astronomers unveiled a discovery that rewrote the map of our cosmic address. The Great Attractor wasn't just a gravitational anomaly, it turned out to be the beating heart of something far grander. The Laniakea Supercluster, a sprawling celestial continent 520 million light-years wide, containing 100,000 galaxies all bound together in a delicate cosmic dance. The name says it all. Laniakea means immense heaven in Hawaiian, and for good reason. If you could see it from above, it wouldn't look like a random scatter of stars, but like a colossal spiderweb with rivers of galaxies flowing along invisible filaments, all converging toward the Great Attractor like tributaries feeding a vast gravitational delta. What makes this structure so revolutionary isn't just its scale, but how it redefines what it means to be local in the cosmos. Imagine standing in a valley where every stream flows downhill toward a central lake that's Laniakea. Every galaxy within its borders, including ours, is part of this slow-motion cascade, drifting toward the Great Attractor at the core. But here's the twist: Laniakea itself is just one thread in an even larger tapestry. Neighboring superclusters like Perseus Pisces and Shapley exert their own gravitational pull, creating a dynamic interplay where these titanic structures jostle for dominance like continents adrift on the ocean of space-time. Visualizing Laniakea feels like peeling back layers of an infinite onion. At the smallest scale, galaxies clump together like fireflies. Zoom out, and those clumps form chains, the filaments of the cosmic web. Zoom out further, and those filaments weave into superclusters, with Laniakea as just one shimmering knot in the grand design, the most mind-bending part. This isn't static architecture. Superclusters are alive with motion, galaxies sliding along their gravity highways at millions of miles per hour, caught in a flow older than time itself. The real breakthrough came when scientists mapped this motion using radio telescopes, tracking the subtle drift of galaxies to trace Laniakea's outline. Like cartographers charting an unseen continent by watching how birds flock toward hidden waters, they revealed boundaries not defined by edges but by movement. Galaxies on one side of Laniakea flow toward its heart, those on the other are tugged toward different superclusters. This makes the Great Attractor less a destination and more a waypoint, a whirlpool in a river that stretches across the observable universe. Why does this matter? Because Laniakea forces us to confront how little we truly grasp about the universe's structure. For centuries, we saw space as mostly empty, with galaxies as isolated islands. Now we know they're threads in a woven tapestry, and the Great Attractor is just one knot in the weave. Every new layer we uncover, From dark matter's hidden scaffolding to these vast supercluster flows, hints that reality is far stranger, far more interconnected than we ever dreamed. And somewhere beyond Laniakea's frontiers, the cosmos stretches on, its full pattern still waiting to be traced. Just as the Great Attractor pulls us in, something equally mysterious is pushing us from the other side, a region so empty its lack of gravity creates a repelling force. Scientists call it the Dipole Repeller, a cosmic void stretching over 1.4 billion light-years where galaxies are scarce and space itself seems to shun matter. If the Great Attractor is a gravitational magnet, the Dipole Repeller is its bizarre counterpart, an expanse so barren that galaxies flow away from it like water rushing downhill, creating a seesaw effect across the universe. Think of it like standing between two massive fans, one blowing toward you, the Great Attractor, the other blowing away, the Dipole Repeller. Our motion through space isn't just about being pulled, it's about being pushed by what's not there. This is the strange paradox at play. While gravity from massive objects drags galaxies closer, the absence of matter in these voids exerts its own weird kind of anti-gravity, courtesy of the universe's expansion. Empty space stretches faster where there's less resistance, effectively shoving galaxies toward denser regions. The discovery of the Dipole Repeller forced astronomers to rethink the cosmic tug-of-war. Earlier models assumed the Great Attractor was the sole driver of our galaxy's motion. But when researchers mapped the velocities of thousands of galaxies, the numbers didn't add up unless they factored in this enormous void's repulsive effect. It's like realizing the river you're floating down isn't just flowing toward a waterfall, it's also being pushed by a vast, slow-moving tide behind you. What makes this even more mind-bending is how these voids fit into the cosmic web. While filaments and superclusters like Laniakea are the universe's bustling cities, voids are its deserts, regions where dark energy dominates, accelerating expansion and leaving behind ghostly fingerprints in galaxy motions. The Dipole Repeller isn't just empty, it's actively shaping the large-scale flow of the cosmos, proving that nothingness can be as influential as the densest superclusters. Yet the Dipole Repeller remains elusive. Unlike the Great Attractor, which we've glimpsed through dust-penetrating wavelengths, this void is defined by what's missing, making it far harder to study. Its boundaries are fuzzy, its influence indirect. Some scientists speculate there could be even larger voids out there, their repulsive forces woven into the universe's expansion like invisible hands sculpting the paths of galaxies. This cosmic push and pull reveals a deeper truth. The universe isn't just a collection of objects, but a dynamic interplay between presence and absence. The Great Attractor pulls, the Dipole Repeller pushes, and caught between them, our galaxy rides a current older than time itself, a reminder that even emptiness holds power in the grand design of everything. Even as we unravel the mysteries of the Great Attractor and Laniakea, an even more unsettling pattern emerges. Galaxies aren't just moving toward these structures. They're streaming in a coordinated flow that defies all expectations, as if the universe itself is tilting toward something unseen. Astronomers call it the dark flow, a phenomenon so bizarre it hints at forces beyond the edges of our observable cosmos. Imagine tossing a handful of leaves into a river, only to watch them all drift in the same direction, not just with the current but against it. That's the enigma we're facing. The dark flow was first detected in 2008 when researchers studying galaxy clusters noticed something impossible. Hundreds of them were all drifting in sync toward a single patch of sky near the constellations Centaurus and Hydra. The same general direction as the Great Attractor, but with velocities that couldn't be explained by any known mass. These clusters, some of them billions of light-years apart, were moving at staggering speeds of nearly 2 million miles per hour, as if tugged by something outside our cosmic horizon. Here's why this shakes the foundations of cosmology. According to Einstein's theory, the universe should expand uniformly after the Big Bang, with matter distributed evenly enough that no single direction should dominate large-scale motion. Yet the dark flow suggests a colossal asymmetry, a gravitational gradient so vast it implies structures beyond what we can see. Picture standing on a beach, feeling the tide pull at your feet, while somewhere beyond the horizon looms an island so massive its gravity bends the ocean itself. The leading theory that the dark flow is evidence of superstructures lurking in the unobservable universe regions so distant their light hasn't had time to reach us in 13.8 billion years. These could be hyperclusters of galaxies or even exotic concentrations of dark matter, warping space-time on scales that dwarf Laniakea. Some models suggest these unseen giants might be relics from the universe's inflationary period, when space expanded faster than light, leaving behind imprints that still tug at everything we know. But the dark flow isn't just a cosmic curiosity, it's a boundary pusher. If confirmed, it means our observable universe, all 93 billion light-years of it, might just be a neighborhood inside something infinitely grander. And the Great Attractor, it could be a mere waypoint in a chain of gravitational dominance stretching into the unknowable. Every new observation peels back another layer, revealing how much of the cosmos remains hidden, not by dust or distance, but by the very limits of time and light. Here's the unsettling truth about the Great Attractor: what we can see doesn't come close to explaining its terrifying grip on the cosmos. Astronomers have crunched the numbers and the results are baffling. All the visible galaxies, gas clouds, and dust in its vicinity add up to less than 10% of the gravitational force needed to account for the way it's hurling entire superclusters through space at breakneck speeds. It's as if you dropped a boulder into a pond, only to watch the ripples move as though the rock were a mountain. Something invisible is amplifying its pull, and the leading suspect is a hidden metropolis of dark matter structures so vast they rewrite our understanding of cosmic geography. To grasp the scale of this discrepancy, picture the Milky Way. Our galaxy's mass, stars, planets, nebulae equals roughly 1.5 trillion suns. Yet the Great Attractor's gravitational influence suggests it holds the equivalent of 50,000 Milky Ways. When scientists tally up every observable speck of light in its direction, they only find enough ordinary matter to match a fraction of that staggering figure. The rest, either there's an entire population of galaxies cloaked behind impenetrable dust clouds, or dark matter's grip is far stronger than we ever imagined. Clues lie in the peculiar motions of nearby galaxies. Like leaves caught in a whirlpool, their trajectories reveal the contours of unseen currents. By mapping their paths, researchers have reconstructed the Great Attractor's gravitational field, and it's far lumpier than expected. Instead of a smooth, concentrated mass, it's more like a sprawling network of dense knots connected by filaments, a hidden architecture where dark matter forms the bones and ordinary matter is just the flesh. Supercomputer simulations support this, showing how these shadowy threads weave through the universe, funneling galaxies toward gravitational nexuses with terrifying efficiency. But the mystery deepens. Even if we account for every possible dark matter halo, the math still leaves a glaring gap. Some scientists speculate there could be entire superclusters lurking behind the zone of avoidance, their light swallowed by the Milky Way's glare. Others propose more radical ideas: exotic particles with strange gravitational properties, or even flaws in our understanding of gravity itself. Einstein's theory has passed every test so far, but the Great Attractor's missing mass problem is a crack in the foundation, a whisper that somewhere in the darkness the rules might be different. What's certain is this: the universe hides most of its weight. For every glowing galaxy we spot, there are mountains of unseen mass shaping the cosmos from the shadows. The Great Attractor isn't just a destination, it's a ransom note, proof that we've barely begun to decode the true ledger of creation. And until we solve its missing mass problem, we're left staring at the sky, knowing most of what holds us captive remains utterly invisible. To understand how we pierce the Great Attractor's secrets, we have to rewind the cosmos to its infancy, a time when the universe was a seething plasma so dense, light couldn't travel an inch before bouncing off particles like a pinball. In this primordial soup, gravity and radiation waged war, creating pressure waves that rippled outward in spherical shells like echoes in a cosmic bell. These weren't just any waves, they were baryon acoustic oscillations, the universe's first sound waves, frozen in time when matter finally broke free from light's grip 380,000 years after the Big Bang. Fast forward 13.8 billion years, and those ancient echoes are still written into the fabric of space. When astronomers map millions of galaxies in projects like the Sloan Digital Sky Survey, they don't see random sprinkles of stars. They find galaxies clustered at a very specific average separation, 490 million light-years apart. That distance isn't arbitrary, it's the exact scale of those primordial sound waves, stretched to cosmic proportions by the universe's expansion. Think of it like finding fossilized raindrops everywhere you dig, each one preserving the same exact size, telling you about the storm that made them. Here's where it gets groundbreaking. By measuring these oscillations around the Great Attractor region, scientists can reconstruct its true gravitational influence, not just what we see, but what's hidden in the dark matter scaffolding. Imagine trying to guess the shape of an iceberg by watching how water ripples around it. The Sloan survey revealed that galaxies near the Great Attractor aren't just randomly scattered. They're draped over those ancient sound wave shells like beads on a string, revealing how its gravity warps the cosmic web at scales we'd never perceive otherwise. This technique does more than confirm the attractor's mass. It exposes the universe's skeleton. Where light fails, baryon acoustics shine, letting us measure distances so vast they make parallax useless. Each galaxy pair becomes a ruler etched with the universe's oldest resonance. And when applied to the Great Attractor, these rulers show something startling. Its pull isn't just local. It's part of a gravitational cascade stretching across superclusters, proving that even the largest structures owe their alignment to whispers from the dawn of time. The real magic lies in what this means for dark energy. Those acoustic rulers aren't static. They stretch as the universe expands. By comparing ancient baryon waves to their modern counterparts, astronomers caught the universe red-handed, accelerating under dark energy's push. The Great Attractor's domain, vast as it is, becomes just one chapter in a grander story, one where the afterglow of creation's first sounds helps us weigh the invisible forces shaping everything. The Great Attractor's gravitational reach might seem immense until you zoom out far enough to see it's just one thread in a tapestry of unimaginable scale. Floating roughly 500 million light-years beyond it lies the Sloan Great Wall, a filament of galaxies stretching 1.4 billion light-years, so vast it would take a beam of light 40,000 times longer than human civilization's entire history just to traverse it. These two cosmic titans aren't just neighbors, they're likely bound by the same web of dark matter, part of a fractal pattern where clusters beget superclusters, and superclusters merge into walls that defy comprehension. What makes this connection so extraordinary is how it mirrors nature's patterns on a galactic scale. Picture a river system, tiny streams feeding creeks, creeks flowing into rivers, rivers merging into continental watersheds. The Sloan Great Wall is the Amazon basin of this cosmic hydrology, with structures like the Great Attractor acting as junctions where gravitational tributaries converge. Astronomers call this the cosmic web, a labyrinth where galaxies cling to dark matter filaments like dew on a spider's silk, with voids stretching between them like gaps in a net. Here's where it gets eerie. When scientists mapped the Sloan Wall's galaxies, they noticed something peculiar. Their velocities hinted at gravitational interactions with the Great Attractor region, as if both structures were nodes in a single, vibrating network. Supercomputer simulations support this, showing how primordial density fluctuations after the Big Bang could have birthed these megastructures in connected chains. It's not just that the attractor pulls us, it's that the wall might be pulling it, creating a domino effect across hundreds of millions of light years. Yet the Sloan Wall is merely the largest known example. Probing deeper with redshift surveys, astronomers keep finding longer, thicker filaments, some stretching 2 billion light-years or more. This begs a radical question. Could the Great Attractor and Sloan Wall themselves be minor features in an even grander pattern, one too vast for our telescopes to currently grasp? The universe seems to repeat its architecture at every scale, from the tiniest galaxy clusters to these staggering walls, all woven together by dark matter's invisible threads. This fractal-like structure forces us to confront a humbling truth. The cosmos operates on scales so enormous that even the Sloan Great Wall might someday seem provincial. Just as Copernicus shattered the illusion that Earth was the universe's center, modern astronomy reveals that our entire supercluster could be a speck in a web whose full design we've only begun to trace. And somewhere in the interplay between these titanic walls and attractors lies the key to understanding why the universe looks and flows the way it does. Our galaxy's journey toward the Great Attractor isn't just a slow drift, it's the prelude to a collision of cosmic proportions. Over the next few billion years, the Milky Way won't simply approach this gravitational giant. We'll plunge straight into its densest region, the Norma Cluster, a crowded metropolis of galaxies swirling at the attractor's core. Picture a snowball rolling downhill, gathering speed until it smashes into a mountainside, except this snowball is 100,000 light-years wide, and the mountain is a gravitational trap with thousands of times our mass. Simulations of this fate reveal something astonishing. Galactic mergers aren't the violent crashes we might imagine. When galaxies collide, they pass through each other like ghosts, their stars so widely spaced that direct impacts are nearly impossible. Instead, gravity weaves them into a slow-motion dance, stretching their spiral arms into ribbons of stardust until they merge into a single, bloated elliptical galaxy. For the Milky Way, this means our familiar spiral shape will warp and blur, our galactic disk shredded by tidal forces as we're absorbed into Norma's embrace. But here's what makes this process so surreal. It's already begun. Right now, invisible tendrils of dark matter from the Great Attractor are tugging at our galaxy's halo, subtly altering the trajectories of stars at the Milky Way's fringes. In about 5 billion years, roughly the same time our Sun will exhaust its fuel, our galaxy and Andromeda will finish their own merger, forming a new hybrid galaxy astronomers call Milky. By then, the combined mass of these two galaxies will already be accelerating toward Norma, pulled by gravity's inexorable tide. The end result, a cosmic Russian doll effect. Milky will become just one of thousands of galaxies orbiting Norma's supermassive black hole, a fate shared by every star system in our local group. Yet even this won't be the final act. Norma itself is falling toward the Shapley Supercluster, meaning our far future descendants, if any survive, might witness their galaxy caught in an endless cascade of mergers, each one stretching across epochs longer than life itself has existed. What's truly humbling is realizing how late we've arrived to this party. The Great Attractor has been funneling galaxies toward Norma for over 10 billion years, long before Earth formed. We're witnessing just a snapshot of a process that will continue long after our star dies, a reminder that the cosmos operates on timelines where even collisions unfold with glacial patience. And somewhere in that distant future, the night sky will bear no resemblance to the one we know today. Its familiar constellations erased, replaced by the glow of a trillion alien suns circling a new gravitational heart. Buried in the afterglow of the Big Bang lies an anomaly so bizarre, it makes the Great Attractor seem almost ordinary, the cold spot. This mysterious region in the cosmic microwave background, the universe's oldest light, is colder than its surroundings by a tiny but statistically impossible margin. At first glance, it might seem unrelated to our galaxy's gravitational plunge toward the Great Attractor, until you realize both defy expectations in eerily similar ways, hinting at gaps in our understanding of cosmic structure. The cold spot spans nearly 1.8 billion light-years, a frigid bruise on the sky that shouldn't exist if the early universe were as uniform as standard cosmology predicts. One leading theory: it's a supervoid, an emptiness so vast that photons passing through it lose energy, like a ball rolling uphill, creating a cold imprint. But here's where it gets wild. The sheer size required would make it the largest void ever discovered, dwarfing even the Dipole Repeller. And if such a void exists, its gravitational absence could subtly alter the trajectories of galaxies, including those in the Great Attractor's flow. Yet the numbers don't quite add up. Simulations show even the largest void shouldn't leave a cold imprint this pronounced. That's led to a far more radical idea, that the cold spot isn't a void at all, but the fingerprint of a collision with another universe during cosmic inflation. Imagine two soap bubbles brushing in a froth of multiverses. The energy drain at their meeting point could leave behind just such a thermal scar. If true, it would mean the Great Attractor's pull isn't just shaped by hidden mass in our universe, but by gravitational echoes from beyond reality's edge. But the most unsettling connection lies in their shared defiance of the cosmological principle, the assumption that the universe is broadly the same everywhere. The Great Attractor's gravitational anomaly and the cold spot's thermal one both suggest a cosmos far lumpier and stranger than we thought, where imbalances persist across unimaginable scales. Whether these two mysteries are directly linked remains unknown, but their existence forces us to confront an unnerving possibility: that what we call the universe might only be a single thread in a tapestry vaster than we dare imagine. What's clear is that both anomalies, one a gravitational maelstrom dragging galaxies, the other a frozen whisper from creation's dawn, are clues written in different cosmic languages. Deciphering their connection could rewrite not just the story of the Great Attractor, but of reality itself. For decades, the Great Attractor remained a ghost, its influence measurable, its form unseen. Then came Chandra, NASA's sharp-eyed X-ray observatory, peering through the Milky Way's obscuring veil to reveal the heart of the mystery. What it found was a cosmic furnace, the Enigma cluster, a swarm of galaxies so densely packed that the gas between them reaches temperatures of 100 million degrees Celsius, hot enough to strip atoms bare and send them screaming across the electromagnetic spectrum as high-energy X-rays. Chandra's images weren't just pretty pictures. Every photon it captured was a clue, painting a portrait of the attractor's hidden skeleton. When gas gets this hot, it glows in X-rays like a neon sign, betraying the presence of mass even when stars and galaxies hide in shadow. By mapping this glow, astronomers could finally weigh the Enigma cluster, and the numbers were staggering. The visible galaxies accounted for barely a fraction of the gravity required to hold such searing plasma in place. The rest, a halo of dark matter so colossal it warps space-time like a bowling ball on a trampoline, bending the paths of galaxies millions of light-years away. But the real revelation lay in the gas itself. Normally, galaxy clusters have orderly, symmetrical X-ray halos like smooth clouds around a mountain. Enigma's was different, twisted, turbulent, as if stirred by some unseen hand. This wasn't just a random collection of galaxies, it was a dynamic system, possibly the aftermath of a colossal collision between multiple clusters. Imagine pouring cream into coffee, then watching it churn from invisible spoons. That's Enigma's gas roiling with the gravitational aftershocks of ancient mergers. Chandra's data did more than confirm the attractor's mass. It exposed how that mass is organized. The hottest gas wasn't centered on the brightest galaxies, but offset, as if the cluster's true heart lay somewhere darker. This misalignment suggests dark matter isn't just an invisible fog. It might have its own structure, clumping independently from the stars we see. It's like realizing a marionette's strings aren't tied to its limbs, but to something lurking just outside the stage lights. Yet even Chandra has its limits. The observatory can map the Norma cluster's core, but the attractor's full reach extends far beyond, into regions where X-rays fade into silence. Every breakthrough peels back one layer, only to reveal another mystery beneath. And somewhere in that interplay between visible fire and invisible grip lies the answer to why our galaxy and 100,000 others are racing toward this cosmic beacon with no way to stop. The Great Attractor isn't some lone titan standing guard over the cosmic highway. It's just one stop in a sprawling network of gravitational waypoints dotting the universe. Picture the cosmic web as an enormous subway system where galaxies ride dark matter rails toward the busiest intersections. Along these routes, nodes like the Coma cluster serve as grand central stations, their immense gravity orchestrating the flow of countless galaxies. While the Great Attractor dominates our local supercluster's motion, it's merely a regional hub compared to monsters like Coma, whose core packs over 1,000 galaxies into a space just 20 million light-years wide, so dense that collisions between galaxies there happen as often as commuters bumping shoulders in a crowded train. What makes these nodes extraordinary isn't just their mass, but their role as cosmic sorting facilities. As galaxies funnel into them, they're stripped of their gas like travelers dropping luggage, their spiral arms unraveling into streams of stars that form glowing bridges between neighbors. The Coma cluster takes this process to extremes. Its central galaxies have been merging so relentlessly that they've formed a single, bloated elliptical giant, surrounded by a haze of orphan stars ejected during close encounters. The Great Attractor's Norma cluster shows similar scars, suggesting that all these nodes operate by the same ruthless rules. Gravity doesn't just pull, it processes, reshapes, and ultimately homogenizes. Yet here's where it gets counterintuitive. For all their destructive power, these nodes are also creators. The same collisions that tear galaxies apart seed their centers with fresh gas, igniting bursts of star formation and feeding supermassive black holes. The Perseus cluster, another heavyweight 240 million light-years away, showcases this duality. Its central galaxy, NGC 1275, blasts out jets of energy powerful enough to sculpt entire cavities in the surrounding gas, while new stars spark to life in the wreckage. The Great Attractor's core likely hosts similar fireworks hidden behind the Milky Way's dust. Zoom out far enough and a pattern emerges. From the relatively modest Norma cluster to the behemoth Coma, these nodes seem to follow a cosmic hierarchy, a fractal where clusters cluster into superclusters and superclusters gather along unfathomably vast walls. Each one leaves its fingerprint on the universe's expansion, creating subtle eddies in the Hubble flow where space stretches slower in their grip. They're not just features of the cosmic web, they're the loom that weaves it, their gravity dictating where filaments thicken and voids expand. And somewhere in the interplay between these titans, between the push of dark energy and the pull of nodes like the Great Attractor, lies the blueprint for everything. Measuring distance in space seems straightforward. Point a telescope. Note how much a galaxy's light stretches toward the red end of the spectrum, and calculate how fast it's moving away from us. But when it comes to the Great Attractor, this simple system falls apart spectacularly. That redshift signal, the universe's golden ruler, gets warped by something called peculiar velocity, the wild card of cosmic motion. Imagine trying to clock a sprinter's speed while they're running on a treadmill aboard a speeding train. The redshift tells you their movement, but not whether it's from the treadmill, the train, or both. Now replace the sprinter with a galaxy, and the train with the Great Attractor's gravitational current. That's the chaos astronomers face. Here's where things get counterintuitive. While the universe expands, carrying galaxies apart like raisins in rising dough, gravity fights back. Galaxies caught in the Great Attractor's pull aren't just drifting with cosmic expansion, they're racing toward it, adding their own dynamic velocity to the mix. This creates a redshift distortion so extreme, galaxies appear closer or farther than they really are. The most dramatic cases, galaxy clusters like Norma, where hundreds of galaxies orbit a common center at thousands of miles per second. Their redshifts don't just shift, they smear like a chalk line dragged sideways. Astronomers call this the finger of God effect, where clusters appear stretched into long, thin shapes pointing directly at Earth, a cosmic illusion caused by their frenzied orbital speeds muddying the redshift data. To untangle this mess, scientists deploy cosmic correction factors worthy of a detective novel. By studying the statistical distribution of thousands of galaxies, they map the average flow of the cosmic web, the background expansion, then subtract it to reveal the hidden peculiar motions. It's like isolating a single voice in a choir by canceling out all other singers. Supercomputers simulate dark matter's gravitational influence, predicting how it should tug galaxies off course, while surveys like 2 mass and 6DF cross-check distances using methods less vulnerable to distortion, like the luminosity of giant red stars or the flicker of supernova. The payoff is profound. These corrections expose the Great Attractor's true reach, showing galaxies far beyond Norma caught in its flow. Some, like our Milky Way, are still inbound, while others have already swung past, slingshotted by gravity like comets around the Sun. This dynamic portrait reveals something startling. The attractor isn't a static trap, but a gravitational whirlpool where galaxies enter, spiral, and sometimes escape, their redshift scars telling the story of a battle between expansion and gravity that's been raging since the dawn of time. Yet even with these tools, mysteries linger. The farther we probe, the more the dark flow of unseen forces complicates the picture, suggesting redshift distortions might be our first clue to structures so vast they bend the rules of cosmic cartography. Every correction peels back a layer, but the universe always seems to hold another beneath. The Great Attractor doesn't just hide behind the Milky Way's starry veil. It has an exact cosmic address, a fixed point in the celestial sphere where its gravitational whispers originate. 250 million light-years away, in the constellation Norma, this invisible leviathan lurks, its position triangulated not by sight, but by the motion of galaxies caught in its pull. Norma, named after the carpenter's square used by ancient builders, feels ironically fitting because studying the Great Attractor requires instruments as precise as any tool, and a vantage point few on Earth can access. Here's why location matters. Norma sits deep in the southern celestial hemisphere, a region best observed from latitudes below the equator. For astronomers in the north, it's like trying to peer at Antarctica from New York, possible near the horizon, but drowned in atmospheric distortion. That's where telescopes like South Africa's SALT, the Southern African Large Telescope, become game changers. Perched on a remote Karoo plateau, SALT 11-meter hexagonal mirror array stares straight into Norma's heart, its instruments tuned to pierce the zone of avoidance with infrared and radio eyes. Without these southern giants, the Great Attractor would remain little more than a gravitational ghost story. But pinpointing its distance wasn't just about geography, it required cosmic detective work. Astronomers used a technique called redshift space distortion, mapping how galaxies behind the attractor appear squashed or stretched in their velocities, their paths warped like cars swerving around an invisible speed bump. By comparing these distortions to models, they pinned the attractor's core to a precise patch of sky near Norma's border with Triangulum Australe, a region crammed with X-ray glowing clusters and twisted radio jets. What's startling is how much this address reveals. Norma isn't some random dot on the map, it's a crossroads. The attractor sits where several dark matter filaments converge, a gravitational nexus that funnels galaxies like water merging in a delta. Telescopes like SALT don't just show us where it is, they capture how it shapes everything around it, bending light and rewriting trajectories across 250 million light-years. And every new observation from these southern sentinels peels back another layer of the mystery, proving that sometimes to uncover the universe's secrets, you need to stand in just the right place on Earth and look up. The Great Attractor's most compelling evidence doesn't come from what we see, but from what we don't. And nowhere is this invisible hand more starkly revealed than in another cosmic spectacle, the Bullet Cluster. This infamous pair of colliding galaxy clusters, 720 million light-years away, became astronomy's smoking gun for dark matter. Like the Great Attractor, it's a place where gravity and light tell wildly different stories, except here, we're watching the drama unfold in real time. Picture two galactic metropolises slamming into each other at 60 million miles per hour. The visible gas superheated plasma between the galaxies crashes like ocean waves, creating shock waves that glow in X-rays. But when astronomers mapped the cluster's total mass using gravitational lensing, the true shock came. The bulk of the gravity wasn't where the gas was. It lagged behind in two distinct blobs that sailed right through the collision untouched. That could mean only one thing: most of the mass was made of something invisible, something that didn't interact with the cosmic traffic jam of stars and gas. Dark matter had left its fingerprint in the wreckage. Now, here's where the Great Attractor echoes this enigma. Just as the Bullet Cluster's gravity defies its visible components, the attractor's pull outweighs every star and nebula we can detect by a factor of 10. Both are cosmic facades, places where the universe's true scaffolding, the dark matter web, betrays itself through gravitational sleight of hand. The difference. While the Bullet Cluster shows this separation in a single, frozen moment, the attractor reveals it across an entire region of space, with hundreds of galaxies acting as tracer particles in a centuries-long experiment. The parallel goes deeper. In the Bullet Cluster, the gas isn't just lagging, it's being stripped away, leaving galaxies oddly naked. Infrared telescopes caught these orphan stars, forming bridges of intracluster light between galaxies like ribbons torn in a storm. Now look at the Norma cluster, the heart of the Great Attractor. Its X-ray halo shows similar turbulence, as if galaxies there have been losing gas for eons. Both systems hint at dark matter's most unnerving trait: it doesn't just hide, it outlasts, preserving structures even as visible matter gets battered and scattered. But the Bullet Cluster offers one crucial clue the attractor can't: a timeline. Because we're seeing that collision mid-event, astronomers can reconstruct exactly how dark matter behaved under extreme conditions. And if the same rules apply to the attractor, where dark matter's pull dominates despite missing visible mass, we're looking at a slower, older version of the same phenomenon. One where galaxies aren't colliding but circling, drawn into a gravitational well that predates most of the universe's history. What ties them together isn't just their composition, but their defiance. Both force us to accept that the cosmos isn't made of what glows, but of what pulls. The Bullet Cluster gave us our first clean snapshot of this truth. The Great Attractor shows us what happens when that truth scales up, when dark matter's whisper becomes a roar, bending the paths of galaxies too numerous to count. And somewhere between these two bookends of cosmic revelation lies the key to understanding why our universe looks, moves, and evolves the way it does. One of the most unsettling discoveries in modern cosmology isn't just about the Great Attractor's pull, it's how its motion might be unraveling our understanding of the universe's expansion. Astronomers call it the Hubble tension, a growing discrepancy between how fast we think the cosmos is growing based on nearby measurements versus observations of the ancient universe. And here's where things get eerie. The Great Attractor's gravitational influence could be throwing a wrench into these calculations, hinting at forces or particles beyond anything in our current physics playbook. The tension stems from two conflicting methods for measuring the Hubble constant, the rate at which space stretches. The first approach studies the cosmic microwave background, the afterglow of the Big Bang, suggesting an expansion rate of about 67 kilometers per second per megaparsec. The second method tracks variable stars and supernova in nearby galaxies, landing closer to 73. At first glance, that 6-unit gap seems trivial, until you realize it's like two clocks ticking at different speeds in the same room. Over billions of years, that tiny disagreement snowballs into a cosmic identity crisis. Enter the Great Attractor. When scientists account for its gravitational distortion of local galaxy motions, the numbers get even messier. Peculiar velocities, those deviations from pure Hubble flow caused by the attractor's pull, skew nearby measurements, like trying to weigh yourself on a scale that's being nudged. Some researchers argue this could explain part of the discrepancy, that we've underestimated how much these regional currents warp our cosmic yardstick. Others think it's a red herring, that even after correcting for the attractor's influence, the tension persists, pointing to something far stranger. This is where the Laniakea model, cosmology's reigning framework, starts to creak. The model assumes dark energy lambda and cold dark matter CDM govern the universe's evolution, with gravity doing the heavy lifting. But if local flows like the Great Attractors can't fully explain the Hubble tension, we might need exotic additions, early dark energy, phantom fields, or even decaying dark matter. Imagine discovering your car's speedometer is off not because of a calibration error, but because the road itself is subtly shifting under your tires. What makes this so thrilling is the Great Attractor's dual role. It's both a confounding variable and a potential key. Its gravitational fingerprints might contain clues to why the universe's expansion doesn't add up. Supercomputer simulations now test whether its peculiar motions align with tweaks to Laniakea or demand more radical overhauls. Every galaxy caught in its flow becomes a data point in this grand experiment, a single note in a cosmic symphony where the tempo keeps changing. And somewhere in that discord, we might find the first hints of physics beyond our wildest theories. The cosmic microwave background, the oldest light in the universe, holds a secret imprint of the Great Attractor's immense gravity. As this ancient radiation from the Big Bang travels across space, it doesn't pass through the cosmos untouched. When it encounters the attractor's colossal mass, the CMB photons get a gravitational wake-up call, subtly distorted by a phenomenon called the kinematic Sunyaev-Zeldovich effect. Imagine sunlight filtering through a stained glass window, its colors slightly altered by the glass, except here, the stained glass is an invisible gravitational field, and the light is the afterglow of creation itself. This effect works like a cosmic scale. As CMB photons plow through the hot gas swirling around the Great Attractor's galaxy clusters, they collide with high-energy electrons. These collisions transfer energy, slightly shifting the photon's frequency, like a ping-pong ball gaining speed when smacked by a paddle. For an observer on Earth, this creates a faint but measurable shadow in the CMB, a patch where the microwaves appear marginally cooler or warmer than their surroundings. The kicker, this shadow isn't random. Its size and depth directly correlate with the attractor's total mass, including all that elusive dark matter. What's revolutionary about this technique is its independence from traditional tools. Unlike redshift surveys or X-ray telescopes, the KSZ effect doesn't rely on visible light or even dark matter's gravitational lensing. It's a direct probe of mass's gravitational fingerprint on the universe's oldest light. Recent data from the Planck satellite and the Atacama Cosmology Telescope revealed these distortions match the Great Attractor's predicted mass to within 5%, confirming yet again that what we see through telescopes is just the tip of the cosmic iceberg. The real magic lies in what this shadow tells us about the attractor's evolution. The KSZ signal isn't static, it encodes motion. By analyzing its asymmetry, astronomers detected the attractor's bulk flow, the collective drift of its galaxies against the CMB's reference frame. This revealed something startling. The attractor isn't just sitting still, pulling galaxies toward it. It's moving too, caught in the gravitational current of even larger structures like Shapley, like a raft swept along by a river we've only begun to map. Yet this shadow also raises questions. Some models predict the KSZ effect should be stronger, given the attractor's estimated mass. The mismatch hints that dark matter might interact in ways we haven't accounted for, perhaps clumping less densely around galaxy clusters than simulations suggest. Or maybe the attractor's gas is hotter, its electrons more energetic, leaving a fainter imprint than expected. Either way, every photon carrying this subtle distortion is a messenger from the edge of our understanding, whispering secrets about the forces that bind the universe and the voids between them. One thing's certain, the CMB isn't just a fossil. It's a living canvas painted over by everything it's passed through in 13 billion years and the Great Attractor's shadow. That's its latest brushstroke, a dark signature waiting to be decoded. The Great Attractor didn't suddenly appear in the cosmos. It was sculpted by gravity from the faintest wrinkles in the newborn universe. Rewind 13.8 billion years, and you'd find only a seething plasma of particles, stretched thin by cosmic expansion. But hidden in that smoothness were quantum fluctuations, microscopic bumps in density no larger than a proton. These imperfections became the seeds of everything, and one of them, buried deep in the future constellation Norma, would grow into the gravitational monster we now call the Great Attractor. Supercomputer simulations like Illustris TNG reveal this transformation in stunning detail. Run the cosmic clock forward, and those initial density variations start snowballing. Dark matter, responding only to gravity, clumps first, forming an invisible scaffold. Ordinary matter, slowed by electromagnetic interactions, trickles into these gravitational wells over hundreds of millions of years. By the time the universe is 1 billion years old, the attractor's precursor is already taking shape, a knot in the cosmic web where multiple dark matter filaments intersect, funneling gas and protogalaxies inward like water swirling down a drain. The real growth spurt happens between 5 and 7 billion years ago, during the universe's most prolific era of galaxy assembly. As smaller clusters merge, their combined gravity creates a feedback loop, pulling in more matter, which amplifies the pull further. Illustris TNG shows this phase vividly. The attractor's core becomes a gravitational traffic jam, with galaxies piling up like cars on a cosmic freeway. Shock waves ripple through infalling gas, heating it to X-ray temperatures visible today in the Norma cluster's searing halo. But here's where simulations reveal something counterintuitive. The attractor's dominance wasn't inevitable. Had those initial density fluctuations been slightly weaker, it might have remained a modest group of galaxies. Slightly stronger, and it could have collapsed into a giant elliptical galaxy long ago. Instead, it found equilibrium massive enough to bend the paths of superclusters, yet diffuse enough to avoid catastrophic collapse. This Goldilocks balance hints at dark matter's peculiar properties, just sticky enough to build vast structures, but not so clingy that it smothers them prematurely. By the time our solar system forms 4.6 billion years ago, the attractor is already ancient, a mature gravitational hub silently steering the Milky Way's course. Illustris TNG's time-lapse shows our galaxy entering its sphere of influence relatively late, like a commuter joining a rush-hour train already in motion. And as the simulation runs into the far future, the attractor's fate becomes clear. It won't stay dominant forever. Dark energy's accelerating expansion will eventually stretch the cosmic web thin, isolating galaxy clusters like islands in an ever-widening sea. But for now, in this fleeting epoch, the attractor reigns a temporary monarch in gravity's grand dynasty, its story written in the slow dance of matter across billions of years. The most unsettling part about the Great Attractor isn't just its pull, it's the growing suspicion that its gravity might be part of something even bigger, a cosmic current stretching beyond the edges of everything we can see. Astronomers call this enigma the dark flow, and it's sparking one of the most heated debates in modern cosmology. Picture standing on a beach, feeling the tide tug at your ankles, only to realize the water isn't just rising, it's being sucked toward some unseen vortex far beyond the horizon. That's the scale of the mystery we're facing. The controversy began in 2008 when a team analyzing hundreds of galaxy clusters noticed something impossible. These colossal structures, some billions of light-years apart, were all drifting in the same direction at nearly 2 million miles per hour toward the same patch of sky near the Great Attractor. What made this discovery so shocking was the sheer scale. According to standard cosmology, the universe should expand evenly after the Big Bang, with no preferred direction for large-scale motion. Yet here was evidence of a coordinated flow defying that fundamental principle, as if space itself were tilted toward some unseen mass lurking beyond our observational limits. Skeptics were quick to challenge the findings. Some argued it was a measurement error, that dust or foreground galaxies were distorting the data. Others suggested the dark flow might just be the tail end of the Great Attractor's influence, its gravity reaching farther than we'd modeled. But when follow-up studies using the Planck satellite's cosmic microwave background data detected the same peculiar motion, the debate exploded. The numbers didn't add up unless there was something out there, a structure so massive its gravity warps space-time across unimaginable distances, tugging at everything in our observable universe like a magnet pulling iron filings. What makes this so radical is what it implies about the cosmos. If the dark flow is real, it suggests the Great Attractor isn't the final destination. It's just one ripple in a river flowing toward an even grander attractor, something beyond our cosmic horizon. Some theorists speculate this could be a relic of inflation, a scar from when the universe expanded faster than light, leaving behind imprints that still shape galactic motion today. Others wonder if we're seeing the gravitational shadow of another universe brushing against ours in the multiverse foam. The most compelling counterargument comes from simulations. When cosmologists model the known distribution of matter, including dark matter filaments and superclusters like Laniakea, they can't reproduce the dark flow's scale without invoking exotic physics or undiscovered structures. This forces an uncomfortable choice. Either our maps of the universe are missing colossal chunks of mass, or our understanding of gravity needs an overhaul. Either way, the dark flow controversy exposes how little we truly grasp about the forces shaping existence. What's at stake isn't just an academic disagreement. If the flow is confirmed, it would mean the Great Attractor is a pawn in a much larger game, one where the board extends into realms we may never observe directly. Every galaxy, every star, every atom in our bodies would be part of a current older than time, flowing toward a destination we can't see. And that realization that the universe might be far more connected, far more directed than we ever imagined, is what keeps astronomers awake at night, staring at data that refuses to fit neatly into any textbook. What if the Great Attractor's gravitational dominance isn't just about what's there, but what isn't? Enter the void connection theory, a mind-bending proposal suggesting that the attractor's pull might be supercharged by the emptiness surrounding it, cosmic voids so vast they act like gravitational drains. Picture a bowling ball placed on a stretched rubber sheet. Normally, it creates a single dent, but if you remove sections of the sheet around it, the ball sinks even deeper, warping the fabric more dramatically. That's the essence of this idea. The Great Attractor isn't just a massive knot in the cosmic web, it's a knot amplified by the voids tugging space taut around it. The prime suspect in this cosmic conspiracy, the local void, a sprawling emptiness stretching nearly 200 million light-years beside our galactic neighborhood. Unlike the Dipole Repeller, which pushes galaxies away, voids like this might enhance the attractor's pull indirectly. Here's how: as dark energy accelerates the expansion of these voids, their edges become gravitational slopes. Galaxies near these borders slide inward, not because the void itself pulls them, but because the surrounding space, stretched thinner by expansion, offers less resistance to the attractor's gravity. It's like rolling marbles downhill where the hill gets steeper because someone dug a pit nearby. Evidence for this comes from peculiar galaxy motions. Surveys show galaxies on the far side of the local void are drifting toward the attractor faster than models predict. Supercomputer simulations that factor in void geometry match these observations eerily well, suggesting voids aren't just passive gaps, they're active players in the cosmic tug-of-war. Some researchers even propose that void arrangements could create gravitational lenses for dark matter, focusing its influence in ways that amplify the attractor's reach. Yet this theory isn't without controversy. Critics argue that void's effect should be negligible over such vast distances, their influence dwarfed by the attractor's sheer mass. Others counter that the cumulative effect of multiple voids, like the sculptor void and microscopium void, could create a feedback loop, their combined expansion tweaking the gravitational landscape like invisible fingers plucking cosmic strings. The implications are staggering. If true, the void connection theory means the Great Attractor's power isn't just about its own mass, but about the universe's hollows reshaping gravity's rules. It's a reminder that in the cosmic web, emptiness can be as sculptural as matter, a hidden chisel carving the paths of galaxies. And if voids really are tuning the attractor's pull, it forces us to ask what other invisible hands might be guiding the universe's grand design. What if everything we've measured about the Great Attractor's pull is wrong, not because of errors in our calculations, but because we've been staring at the cosmos from inside a cosmic hall of mirrors? Enter the KBC void, a colossal bubble of emptiness 7 times wider than average galactic voids, with our Milky Way sitting uncomfortably close to its center. This isn't just any empty patch of space, it's one of the largest underdense regions in the observable universe, and our position within it might be warping our perception of reality itself, from the attractor's true influence to the very expansion rate of the universe. Here's the paradox in action. Imagine you're standing at the bottom of a deep well, trying to judge the distance to nearby trees. Your perspective is skewed. Objects appear farther away than they really are because of the walls distorting your view. Now replace the well with the KBC void, a spherical region roughly 2 billion light-years across where galaxies are strangely scarce, and the trees with galaxy clusters like the Great Attractor. Because we're embedded in this vast emptiness, the usual rules of cosmic measurement break down. The void's low density means space inside it expands faster than the dense outer regions, causing galaxies beyond its borders to appear as if they're receding unnaturally quickly. This could explain why local measurements of the Hubble constant, the universe's expansion rate, clash with those taken from the early universe, a discrepancy known as the Hubble tension. The implications for the Great Attractor are profound. If the KBC void is artificially amplifying our perception of cosmic expansion, then the attractor's gravitational pull might be stronger or weaker than we've estimated. Normally, peculiar velocities, galaxies deviating from uniform expansion, are used to map large-scale flows like the attractors. But if those velocities are being skewed by the void's underdensity, we could be misjudging the attractor's mass or even its distance. Some models suggest the void's effect might exaggerate the attractor's influence by up to 15%, making it seem like a more dominant player in our local universe than it truly is. But the KBC void isn't just a measurement headache, it's a statistical anomaly. Structures this large shouldn't exist under standard cosmology. Simulations of the cosmic web predict voids rarely exceed 1 billion light-years, yet the KBC spans nearly twice that. If confirmed, its existence would force us to reconsider how matter clumped together after the Big Bang. One radical theory posits that the void isn't random. It's the imprint of an ancient collision with another universe during inflation, leaving behind a bubble of distorted spacetime. The real twist: the KBC void might solve one mystery while creating others. If it's warping our view of the Great Attractor, then what else are we misreading? The so-called dark flow of galaxies moving in unison could be an illusion, a reflection of our off-center vantage point rather than evidence of unseen superstructures. Even the cosmic microwave background's temperature fluctuations might carry shadows of this void's influence, subtly altering our entire cosmic frame of reference. For now, astronomers are racing to map the KBC void's boundaries with next-generation surveys like the Dark Energy Spectroscopic Instrument (DESI, which can measure galaxy densities in 3 dimensions. Each new data point peels back another layer of the paradox. Are we truly floating in a rare bubble of nothingness, or is the universe playing a trick on us, using emptiness to mask its deepest secrets? One thing's certain: until we escape the void's gravitational hall of mirrors, the Great Attractor's true nature might remain just out of reach. Right now, we're standing on the brink of a revolution in how we see the unseen, and the Great Attractor is ground zero. The next generation of sky-scanning giants like the Vera C, Rubin Observatory's Legacy Survey of Space and Time (LSST), and the European Space Agency's Euclid Telescope are about to rip away the cosmic veil with tools so precise they'll map dark matter's invisible scaffolding like never before. Imagine swapping grainy black and white footage for Ultra HD. That's the leap we're making. LSST 8.4-meter mirror perched high in Chile's arid Andes won't just take pretty pictures. Every few nights for a decade, it'll capture the entire southern sky in staggering detail, spotting galaxies so faint they're practically ghosts. But the real magic lies in weak gravitational lensing, the subtle warping of those galaxies' shapes as their light passes through the Great Attractor's dark matter tendrils. Like watching streetlights distort through a glass of water, these tiny bends reveal the attractor's hidden mass distribution down to a precision of 1%. That's enough to distinguish whether its core is a smooth halo or riddled with subclumps, each a fossil from ancient cosmic collisions. Meanwhile, Euclid's orbiting eye offers something even more radical: infrared vision combined with razor-sharp optics, free from Earth's atmospheric blur. While LSST scans from the ground, Euclid will hover at Lagrange point 2, a million miles into space, charting the attractor's domain in 3D, its secret weapon. Spectroscopy, splitting starlight into rainbows to measure redshifts with pixel-perfect accuracy. This lets astronomers reconstruct not just where dark matter lurks, but how it's moving, tracing the attractor's gravitational currents like dye swirling in water. Together, these telescopes form a tag team of cosmic detectives. LSST wide-field surveys will catch the big picture, how the attractor bends light across millions of galaxies, while Euclid's deep dives pinpoint individual dark matter filaments with the clarity of an MRI scan. Early simulations suggest they might even spot dark galaxies, clumps of pure dark matter devoid of stars, lurking in the attractor's outskirts. These invisible islands could rewrite our understanding of how structure forms, proving that what we call empty space is anything but. But the real payoff could be even stranger. Some theories predict dark matter isn't just cold and collisionless, it might interact weakly with itself, creating faint friction within the attractor's halo. If LSST and Euclid detect unexpected smudges in their lensing maps, it could mean dark matter has a hidden physics, a shadow version of electromagnetism we've never seen. That's the tantalizing promise of these missions. They're not just mapping the attractor's present, they're decoding 13 billion years of cosmic history, one bent photon at a time. By the mid-2030s, the data deluge will begin. Petabytes of observations fed into supercomputers running algorithms trained to spot patterns no human eye could discern. The attractor's missing mass problem might finally crack open, revealing whether it's fed by hidden superclusters, exotic particles, or something beyond our current math. And when it does, we won't just solve a mystery, we'll redefine our place in a universe where most of the action happens in the dark. Could the Great Attractor's inexplicable pull be a cosmic breadcrumb evidence that our universe isn't alone? A fringe but electrifying theory suggests this gravitational anomaly might not belong to our reality at all, but to a parallel one brushing against ours in higher dimensional space. Theoretical physicist Laura Mersini-Houghton made waves with her radical proposal that the attractor's strange motion, along with other large-scale anomalies like the cold spot, could be gravitational echoes from a neighboring universe. Picture two soap bubbles floating close together, their surfaces nearly touching where they press against each other. The fabric of each bubble dimples slightly. If our universe is one such bubble, the Great Attractor might be that dimple, a place where another realm's gravity bleeds through the membrane of space-time. Mersini-Houghton's math points to eerie symmetries. Her models of cosmic inflation, the universe's explosive early expansion, predict that quantum fluctuations at the birth of time should have left specific imprints on large-scale structure. Among them, a preferred direction in the cosmos where gravitational forces appear misaligned with the rest of the universe. When she mapped these predictions against real observations, the alignment was uncanny. The so-called axis of evil in the cosmic microwave background points unsettlingly close to the Great Attractor's location. Even more provocative, her work suggests that if another universe's gravity were tugging ours, it would create exactly the kind of coordinated galaxy flows we call the dark flow. Critics counter that multiverse theories are untestable by nature. You can't observe what's outside your own universe, but Mersini-Houghton argues subtle fingerprints remain. If the attractor's gravity were leaking from another dimension, its influence should taper off in specific mathematical patterns rather than following standard gravitational decay. Some astronomers claim to have detected these telltale signatures in galaxy surveys, though the data remains hotly disputed. Others note that the attractor's region has an unusually high concentration of spinning galaxies aligned in the same direction, as if some external torque were twisting spacetime itself. The most tantalizing clue might come from quantum entanglement. In the bizarre world of particle physics, entangled particles instantly influence each other across arbitrary distances, a phenomenon Einstein dismissed as spooky action at a distance. Mersini-Houghton proposes that universes born from the same quantum fluctuation could remain similarly entangled, their gravitational fields subtly linked. In this view, the Great Attractor isn't pulling us. It's the shadow of a sister universe pulling its own version of our galaxy, with the connection transmitting through higher dimensions like vibrations across a spiderweb. Even if the multiverse theory falters, it's reshaped how we frame cosmic mysteries. The attractor's oddities force us to question whether missing mass is really missing, or just hiding in plain sight, folded into dimensions we can't perceive. Future telescopes hunting for primordial gravitational waves might catch whispers of these boundary crossings, ripples from collisions between universes we'll never see directly. Until then, the Great Attractor remains a riddle wrapped in an enigma, a gravitational siren call that might be either the weight of the unseen or the tug of the unknowable. The Great Attractor doesn't just exist in the realm of science, it's also become a haunting presence in science fiction, bending narratives as powerfully as it bends galaxies. Take Lou Sixon's The Three-Body Problem, where the attractor isn't just a gravitational anomaly but a cosmic harbinger, a lurking force that reshapes humanity's understanding of the universe's ruthlessness. In the novel, the attractor's pull becomes a metaphor for inevitability, a reminder that no matter how advanced a civilization becomes, it's still subject to the indifferent tug of cosmic forces. It's a dramatic leap from reality, but not as far as you'd think. While the real attractor won't trigger apocalyptic alien invasions, its unseen influence does force us to confront our fragility in a universe governed by invisible giants. Other stories take even wilder liberties. In the Mass Effect video game series, the attractor is reimagined as a trap set by ancient machines to harvest civilizations, its gravitational pull masking a deadly secret. The science here is pure fantasy, but the underlying fear is real, that the universe's grand structures might hide agendas beyond our comprehension. Even Star Trek dipped into this dread with the Great Barrier, a mysterious region near the galaxy's core echoing humanity's unease with the unknown lurking behind the Milky Way's dusty veil. Yet the most fascinating portrayals blend fact with fiction. Interstellar's depiction of Gargantua, a supermassive black hole, borrows from the same existential awe that the Great Attractor inspires, a reminder that gravity isn't just a force but a storyteller shaping the fate of everything it touches. While Hollywood amps up the drama with wormholes and time dilation, the real attractor's slow, inevitable pull is no less epic when you grasp the scales involved. Entire galaxies, including our own, locked in a dance that will outlast every star they contain. What these stories get right is the scale of the mystery. The attractor's true power lies in its ability to defy easy explanation, to linger at the edge of our understanding like a shadow just outside the firelight. Science fiction amplifies that unease, turning cosmic curiosity into existential dread. But reality offers its own chilling twist. Unlike fictional villains, the attractor isn't malicious. It doesn't want anything. It simply is a reminder that the universe operates by rules we're only beginning to decode, and that sometimes the most terrifying forces are the ones that don't even know we exist. The Great Attractor's gravitational grip might defy explanation for a reason far stranger than missing mass. Our understanding of gravity itself could be incomplete. While Einstein's general relativity has predicted cosmic phenomena with uncanny precision for over a century, its rules break down at the quantum scale where particles flicker in and out of existence. Some theorists propose that the attractor's anomalies, its inexplicable pull, the dark flow of galaxies might be the first hints of quantum gravity's influence on cosmic scales, a shadow of the universe's tiniest workings writ large across the heavens. Imagine if gravity weren't just a smooth warp in space-time, as Einstein described, but a force carried by discrete particles called gravitons. In this quantum framework, gravity could behave differently in regions of extreme density or vast emptiness, precisely the conditions around the Great Attractor. Supermassive galaxy clusters like Enigma might act as cosmic laboratories, their immense gravitational fields magnifying subtle quantum effects normally invisible to our telescopes. One provocative hypothesis suggests that dark matter itself could be an illusion, a mirage created by gravity, leaking into extra dimensions at these massive scales as predicted by string theory. The most tantalizing clue lies in the attractor's gravitational lensing patterns. When light bends around massive objects, general relativity predicts a specific distortion profile. Yet some observations of background galaxies near the attractor show subtle discrepancies, tiny kinks in the lensing arcs that resemble the frothiness of quantum foam, the turbulent spacetime fabric theorized to exist at the Planck scale. If confirmed, these irregularities could imply that space-time isn't perfectly smooth but pixelated, with the attractor's gravity revealing its underlying graininess like a magnifying glass held over a digital image. Critics argue these anomalies could stem from conventional sources, undetected gas clouds, or errors in modeling the Milky Way's dust. But supporters point to a curious coincidence. The attractor sits near the axis of several large-scale cosmological anomalies, including the CMB's cold spot and the mysterious alignment of quasars' rotation planes. This clustering of oddities in one celestial neighborhood suggests a deeper link, perhaps a region where the quantum and cosmic realms intersect more visibly than elsewhere. The implications are staggering. If quantum gravity leaves fingerprints on the attractor's scales, it could bridge the last great divide in physics, uniting the infinitely large with the infinitesimally small. Future gravitational wave observatories, like the proposed LISA space array, might detect ripples in space-time from the attractor's core with enough precision to spot deviations from Einstein's predictions. Until then, this colossal enigma remains both a gravitational marvel and a potential Rosetta Stone, whispering secrets about a universe far stranger than relativity alone can explain. Picture a future so distant that all stars have burned out, galaxies have dissolved, and the universe itself grows cold and dark. In this unimaginable expanse of time, trillions upon trillions of years from now, the Great Attractor's gravitational grip will still linger, a phantom hand sculpting the last motions of matter before the cosmos fades into stillness. Even as dark energy accelerates the universe's expansion, tearing most structures apart, the attractor's influence will persist on a local scale, binding the Milky Way's remnants to its fate in ways that defy intuition. Right now, the local group, our galactic neighborhood, including Andromeda and dozens of smaller galaxies, is locked in a slow-motion merger, destined to collide and form a single, massive elliptical galaxy astronomers call Milky. But this new hybrid won't drift aimlessly. Simulations tracking the attractor's pull over cosmic eons reveal an astonishing trajectory. Even as the universe expands, our merged galaxy cluster will continue falling toward the Norma cluster, the attractor's core, drawn by gravity's unrelenting whisper. Here's where physics gets surreal. Normally, dark energy's repulsive force dominates at large scales, flinging galaxies apart. But within gravitationally bound structures like the Laniakea Supercluster, gravity still holds sway. Over the next 100 billion years, Milky and the attractor's other satellites will complete their inward spiral, merging into a gargantuan, dead galaxy at the center, a dark orb of aging stars, black holes, and frozen planets, orbiting a supermassive black hole with the mass of 100 billion suns. Yet this isn't the end. As protons, the building blocks of atoms, begin decaying in 10 to the 34th power years, a 1 followed by 34 zeros, even this grim structure will erode. Black holes will evaporate via Hawking radiation, leaving behind a diffuse haze of subatomic particles. Through it all, the attractor's legacy remains. The geometry of its gravitational well will subtly skew the distribution of this decaying matter, like a spoon's indent in a bowl of ash. The ultimate irony, in the universe's final moments when time itself loses meaning and only photons and neutrinos drift through infinite emptiness, the last detectable structure might still bear the attractor's fingerprint, an imperceptible gradient in the fading glow of the cosmic microwave background, marking where space once curved toward a forgotten titan. Long after every star dies and every black hole vanishes, the echo of its pull will linger, etched into the fabric of a universe that has forgotten how to remember. We like to imagine ourselves as the protagonists of the universe, the center of our own cosmic story, but stand at the foot of the Great Attractor's influence, and that illusion shatters like glass against bedrock. Every decision in human history, every war fought, every work of art created, has taken place on a speck of dust caught in a gravitational current older than life itself. Our entire civilization exists on a planet orbiting one star among 400 billion in the Milky Way, which itself is just one of 100,000 galaxies being pulled toward an invisible point in the darkness. The scale isn't just humbling, it's almost absurd. Consider this. The 14 million miles per hour we're hurtling toward the attractor means that in the time it takes you to watch this video, Earth will have traveled over 300,000 miles through space, not from its orbit around the Sun, but as part of a much larger voyage dictated by forces we can't see or control. And yet, here we are, tiny, hairless apes on a fragile rock, somehow smart enough to map this journey. That's the beautiful paradox of studying cosmic megastructures. The more we grasp our insignificance in the grand scheme, the more remarkable it becomes that we can comprehend it at all. This is where science transcends mere data points and becomes something almost spiritual. The same tools that measure the attractor's pull, radio telescopes, X-ray observatories, gravitational lensing algorithms, are also mirrors reflecting back our own curiosity and ingenuity. When 19th century astronomers first noticed peculiar galaxy motions, they lacked the technology to explain them. Today, we're unraveling dark matter's secrets and debating multiverse theories to account for these anomalies. Our knowledge has expanded, but so has the depth of the mystery. Every answer about the attractor spawns new questions, revealing how much we still don't understand about the fabric of reality. Perhaps the most profound lesson isn't about the cosmos, but about time. The light we're seeing from the attractor's region left 250 million years ago, when Earth's continents were jammed together in Pangaea and the first dinosaurs were evolving. By the time our descendants witness whatever lies beyond it, if anything, humanity may be unrecognizable. To study such structures is to engage in a conversation across epochs, using mathematics as our universal language. And somewhere in that dialogue between the immensity of the universe and the spark of human intellect, we find a rare kind of balance, a reminder that while we may be inconsequential in scale, our capacity to wonder and explore makes us extraordinary. The Great Attractor doesn't care about us. It won't pause its gravitational march for our telescopes or theories. But in our stubborn insistence to chart its influence, to decode its whispers from the void, we assert something quietly revolutionary, that even the mightiest forces in existence can be measured, questioned, and known. Not controlled, never that, but understood, piece by luminous piece, until the cosmos feels just a little less alien. And for a species adrift in the cosmic dark, that's enough. From the Great Attractor's shadowy grip to the cosmic voids that amplify its pull, these 30 revelations have peeled back the layers of one of the universe's most perplexing enigmas. We've traced the invisible rivers of dark matter that guide entire superclusters, witnessed how our galaxy is caught in a gravitational current older than Earth itself, and grappled with the unsettling possibility that even the attractor might be a pawn in a larger game, a waypoint in a flow stretching beyond the observable cosmos. Yet for every answer, a dozen new questions emerge. Why does the attractor's mass defy our calculations? What lurks in the uncharted depths of the zone of avoidance? Could its anomalies hint at undiscovered physics or even realms beyond our own? The beauty of this mystery lies in its humility. It reminds us that the universe is under no obligation to make sense to us, that even our most advanced tools can only glimpse fragments of a tapestry woven across billions of light years. The Great Attractor isn't just a destination, it's a mirror reflecting how much we've yet to learn. Every galaxy pulled toward it carries a story written in gravity and time, and we're only beginning to decipher the language. What comes next, as telescopes like Euclid and the Vera Rubin Observatory pierce deeper into the dark, we might uncover structures that dwarf the attractor or particles that rewrite the rules of gravity itself. Perhaps future astronomers will laugh at our primitive maps or stand in awe at how much we guessed right. But one thing is certain, the cosmos thrives on wonder. So the next time you look up at the night sky, remember, you're not just staring at stars, you're witnessing a single frame in an epic billions of years in the making, a story where the Great Attractor is but one captivating chapter. And the most thrilling twists, they're still ahead.